Hello, good afternoon, everyone. It's my great pleasure to welcome you to the reboot of our seminar series. I guess this is the lockdown edition. Philani has set up the roster of upcoming seminars, and we also have representation from SASOL looking to join us at some time soon as well. So we'll also get that industry thread going like we had before. And then I know I did it by email, but please let me take this opportunity again to congratulate Mopedi on receiving confirmation of his PhD acceptance. So he'll be graduating in the upcoming ceremony. So please join me in congratulating him.
Yeah, big congrats to him.
I'd also like to extend our congratulations to Dilincha. So as many of you know, Dilincha is applying the stable marriage algorithm to our work in industrial symbiosis. And I guess a natural outcome of that is her getting married. So her commitment to her research is an inspiration to us all. Right. In terms of today's topic, Philani, you've been working on industrial data, the size of industrial data for some time now, and looking at training neural networks on an industry scale of data. And with industry data, there's lots of repetition in there, and it's not clear completely which variables affect which outcome. So this, I think, is kind of a timely PhD study, which can help us optimize the size of our sample and improve how easily we can create ANN models there. So with that, I hand you over to Philani.
And thank you, Prof. Just to add on regarding the seminar presentation. So the roster is up. I think, I don't know whether all of you guys are added to the group, to the folder. Have you guys seen the folder in the Dropbox folder for the seminars?
We can just send the link around because it's an unrestricted access to that link. So if you can just send that link to the Dropbox folder, then maybe post it on the calendar entry.
Okay, all right, I'll do so. Okay, I'm just having, you guys can hear me clearly because it's giving me your network bandwidth is low here. Maybe, but can you guys hear me clearly?
Yep.
Okay, all right, let me just share my my screen, you guys.
By the way, no objections if I put this out on a playlist on YouTube.
Okay, yeah, no objections, but
I think the criticism time, we won't include that presentation criticism time in that. We'll edit that part out. But in terms of the actual content, yeah, I'd like us, our group to have this kind of rolling record of our seminars.
Oh, okay.
Just the content, not this part here.
All right, just share screen. Okay, right, can everyone see the screen properly?
Yes, thanks.
Okay, all right, thank you so much, Prof. So in today's presentation, I'll be going through feature selection for regression in machine learning models. This was something that I encountered as a result of an issue that I was facing in my research work, where I was trying to model this reactor system, and I tried different models. I've had all the features ready, and when I was training this machine learning model of this artificial neural network to predict the pressure, the rate of change in pressure and temperature, my models were just were going way off. And I was not even, I was not understanding why, it was doing so. And then, after, looking up and doing some, background search, if other people were encountering the same issue, that was when I came upon the concept of feature selection. Now, just an introduction. So as you know, recent developments in big data have given us more access to not only data that is richer, but also data that is very highly dimensional. There's this big movement for the fourth industrial revolution. Data is more easily capturable, it's easier to access large streams of data, many devices. Even your cell phone itself, it's not only, it has many meters. Your cell phone has a GPS, accelerometer, gyrometer. It has, all these little sensors that are capturing data on a regular basis. And, as a consequence of this, there's this thing called there's been a significant improvement in the relevance of database model. And, it is evident today, there's a big drive for the, data science, applying of machine learning in solving a lot of the problems that are faced, in corporate settings, in humanities and so forth. But then the thing is, there's no such thing as free lunch. More data, even though we're getting richer data, higher dimensional data, more data equals the existence of, noisy, useless features being collected by the different sensors and methods. So what this means, yes, we are collecting a lot of data, but when you are modeling for a particular reason. There's a particular variable that you are modeling for, and the existence, you having a lot of data does not necessarily mean that you can effectively model that dependent variable. Actually, that your data can actually work against you, and can actually result, as you can see, can have a negative influence on the accuracy of your model, which was the issue that I faced. So I had a lot of data. I had a reactor system. There were, I think, about 15 sensors in the reactor, and I was using all those 15 measurements to predict, temperature and reactor change in temperature and change in pressure. But those, that rich data was actually the negative influence in the accuracy of my models. Another thing, large streams of data also, demand a lot of computational resources, which was an issue that I was facing. I had a lot of data, and just to train, it was taking maybe 2 to 3 days to train my machine learning model to get predictions. And these are the problems, these are the issues that make feature selection a critical process in any machine learning pipeline. Now, what is feature selection? So feature selection, it can be defined as a process by which a data scientist, they select either automatically, which is what I want to achieve for my research work, or manually a subset of relevant features to use in a machine learning model. Yes, we accept that, okay, we have a lot of data, but we want to use data that is relevant to that particular variable, in my case, a process variable that you want to model. And you want to achieve this by the removal of irrelevant and redundant and noisy features from the data set. Noisy in a sense that it is not actually it's not assisting you in any way in the prediction of this, you can say, target variable that you want to model. So, and when you remove this data, you want to remove this, but by removing this, you still want to preserve a small subset of the features from this, you can call it a feature space, that are relevant for this variable being modeled. And, effective feature selection, if you can effectively select the relevant features. For example, when I was modeling the rate of change in reactor temperature. So if I can effectively, because I had the reactor pressure, the feed flow rate, I had the composition of the feed in the reactor, and so forth. And by effectively selecting the relevant features, this significantly reduced the computational complexity of the machine learning model. It also can results in improved model accuracy and increase how well you can interpret the model. Now, why should you select features? Just to delve deeper, the more I grew up with this. When I was introduced to this this field of machine learning and data science, it's a misconception that you get fed. You are fed this misconception that the more data features you have, the better the resulting model is going to be. That this statement is not always true, as I've witnessed in my work. And that is because, as I've explained, data does sometimes include irrelevant, redundant features, and these features don't result in better predictions. And doing this, doing feature selection, it can result in simpler models that are easier to interpret. And when you look at it, it is much easier to understand an output model that uses 10 variables than an output model that uses 100 variables. There's this problem, especially with machine learning models, that they are very black box. You can't actually really, yes, it models the relationships, but you can't interpret them. So through feature selection, now that's there's another area of machine learning that is growing, the interpretability of machine learning models. And this is one of the steps that are allowing us, that are taking us closer to being able to interpret them. And most importantly, shorter training time, which is very important, particularly in a research. If you want to get in a research, you want to get your research results quicker, and in a business setting where you want to have a model as quick as possible, and the model should be accurate and interpretable. Now, just gonna go through the different types of feature selection methods that are currently available. And in today's presentation, I'm just going to focus more on the filter methods. So there's the filter methods and the wrapper methods. Now, filter methods, you actually came across these methods in Matric. If you did stats in Matric, as I will go through some of them, you will actually realize that you came across this. So filter methods, they are based on the characteristics of the features, the characteristics of the data. So they usually have a particular metric, and then you compare, based on the metric, you have your dependent variable, the variable that you want to model, and then you have the features, and then you describe how well the feature relates with this variable that you want to model. They don't use any machine learning algorithm. So, in wrapper methods, they use machine learning. They don't use any machine learning algorithm, in a sense that for determining how well the features describe the variable, there's no machine learning algorithm involved in that process. It's just particularly on the characteristics of the data and the relationships between the features and the dependent variable that you want to model. They're very well suited for quick screen and removal of irrelevant features. So they're very quick. They're not very computationally expensive. They're very easy to present and interpret, and they allow you to really quickly remove irrelevant features on the fly. Now you have the other type are wrapper methods. So wrapper methods, the reason why they're called wrapper methods is because they are wrapped around the machine learning model that you are working on. So they are based on the machine learning model. So what do? They actually consider the feature selection as a search problem. So on one side, you have your machine learning model, and then through that machine learning model, you want to search. So you keep trying different combinations of your different features until you find the combination that best describes that through the machine learning model help you to best describe your target variable. So you basically uses the predictive machine learning algorithm to select the best feature. So particular aspects, so you can have an artificial neural network, and then it becomes a search problem. Maybe you have 15 features. So then from the 15 features, you can ask yourself, which are the 5 best features that best describe your target variable. So then you try different combinations of these 15 features until you find the top 5 that best describe your target variable for that particular machine learning model. And as you can see, once there's search, then of course it starts becoming very computationally expensive. There's many permutations, but however, they do provide the best performing feature subset for a given machine learning algorithm. And they're really big, so I want to cover those at a different stage, because right now I'm also still applying them and working through them for my research work. So just to take a look at the different machine learning methods. So okay, I don't know, I think there's a slide that's went missing here. I don't understand why. Okay, sorry about that. I think I mistakenly deleted a slide when I was okay. So the first one is Pearsons correlation. So you've come across this in high school. You've come across this, I think, in university in stats. This is your R-squared value. So this is it's a very popular method. It's frequently used in machine learning, and it's used to summarize the strength of a linear relationship between 2 data variables. And then it gives you a value that varies between 1 and -1. So as you can see, it's a relationship between 2 data variables. So on one axis, you have a set of features, and then you want to check what's the linear relationship between your feature and the target variable that you want to model. And of course, as you remember, 1 means a very strong positive correlation, and -1 means a very strong negative correlation between the 2 variables, and 0 means there's no linear correlation that exists between the 2 variables. And ideally, in a machine learning perspective, so you have, as I'll show in a diagram later, you have your set of your features, and then you compare the relationship between each of the features to your target variable. And then ideally you want the features that have a high R-squared value and a very low one that are close to +1 and -1. What that means is that those features really have a strong positive correlation or strong negative correlation to that target variable that you want to model. And those are the features that you want to select when you develop your machine learning model. Those will be your input for your machine learning model for modeling that output. 0, of course, means there's no linear correlation between the 2 variables. It means, and then that basically indicates that either those features are redundant or they're just noisy features that don't actually help you in predicting that target variables. Now, Pearsons correlation, it does come with assumptions. The major assumptions are that both variables are assumed to be normally distributed. That is both the feature and the target variable, and a straight line relationship between the 2 variables exists. It assumes there's a straight line relationship. And it means that it also assumes that data is equally distributed around the regression line. And this does have some issues. So you have to be careful when you use this correlation, because when you get in real world, it's very rare that you get data that is really normally distributed. In most cases, relationships are very nonlinear. So you get cases like what I had in my research work. I'd have a variable, it shows to have a very low R-squared value, but then when I omit it from my machine learning model, then there's a high error. But because they assume that this it assumes a straight line relationship. That means that even though there is a nonlinear relationship, the Pearsons correlation didn't pick it up. So before you use it, you try to ensure that try to check whether your data is maybe very closely normally distributed, and that whether check whether it does exist some form of straight line relationship between all the features and the target variable. Another correlation which is more useful than the Pearsons is the Spearman's correlation, and as well it varies between +1 and -1, but then now this one assumes monotone, whether an increase in one variable also results in an increase in another, or whether a decrease in one also results in a decrease in another. So, whereas Pearson's correlation assesses linear relationship, Spearman's correlation, assesses monotonic relationship, whether it is linear or not. And the good thing about Spearman's rank is that it doesn't carry any assumptions about the distribution of data. And as you can see, it describes whether an increase, whether there's relative increases and decreases in the data, and whether there is the linear or non-linear, it is able to effectively describe that. And just to show you, I'm just going to go through the procedure of how it works. So this is how for both Spearman correlation and Pearson's correlation, this is how you usually present the relationship between the variables. So as you can see, on these are all the features here. And this is from what I'm currently working with. So this is a control valve for cooling water. That's the feed flow rate, reactor pressure, reactor level, reactor temperature, cooling water. And these are the components. And then my target variables, of course, are the rate of change in pressure, rate of change in the level, rate of change in the temperature in the reactor, and rate of change in the cooling water that exits the coil. So now, and as you can see here, what this means is, I look at my feature. So I say here, okay, this is rate of change in pressure. So which are the variables that really really have a significant influence in describing the relationship between these two variables, between the features and the rate of change in the pressure. So as you can see, the control valve, it doesn't really have a very strong, it's a 0.4 and so forth. But as you can see, the temperature, the reactor temperature has a very strong inverse relationship. The cooling water temperature as well has a very strong inverse relationship. And, the composition doesn't really have. So, and here, even though, you use your discretion. So even though here, it's not a very strong relationship, but because it's close to the 0.5 mark, you could take it as a result of the non-linearities, but it more or less shows that there exists some sort of relationship between these. So in this instance, you would like to take the temperature and the cooling water temperature, and you would like to take the feed and the pressure and the control valve as the features. Out of all these features, you can take these as the more relevant features for modeling the rate of change in pressure. But then now there's another issue that you need to be careful of, where if I know you guys have from the chemical engineering background, especially in principles, you've worked on the degrees of freedom analysis, where if for example, I think one good example is composition. So if you have, for example, 1, 2, 3, 4, 5, 6 compositions in a feed, actually 5 of them are independent. The last one is 1 minus the compositions of the other. And if you have this one here, it's actually it's related to these, so it's redundant in having this. And a similar thing does happen if there's a correlation between two variables. For example, here there's a strong correlation between the pressure and the feed. which also could be a reason why, as you can see, they also have a similar relationship with the rate of change in pressure. And what this means is that because they have a strong correlation with each other, it's not it's no use having both of them, because both of them describe or relate to this target variable in the same way. So then in that case, you're going to have to eliminate one of them. Ideally, you will eliminate the one that has a stronger correlation with the pressure. But then in this case here, you usually take it to the third and the fourth decimal place, and then you find the one that actually has a stronger correlation there. Another variable that that can be eliminated is the control valve as well. As you can see, the control valve is very strongly correlated to both the temperature of the reactor and the cooling water temperature. Okay, and then as well, because of the strong correlation between this as well can be eliminated. And as well, as you can see, there's a strong correlation between the temperature of the reactor and the cooling water temperature, and same situation as with the feed flow and the pressure. One of them have to be eliminated. And as you can see, the cooling water the reactor temperature has a stronger correlation with the rate of change in pressure, so this has to be eliminated. So ideally, at the end, you just have three variables, which are in this case either the feed flow or the pressure, and the temperature of the two variables, the feed flow pressure and the temperature. And I'm still running simulations on this, but so far I'm getting more accurate models by just using these two variables to model the rate of change in the reactor pressure. So yeah, I think this was the intention of this presentation, just to introduce you to the filter method, just to present how you can use a filter method in selecting features for modeling a particular target variable using machine learning model. And then the same procedure is repeated for here. The variables I'm working with are the rate of change in pressure, rate of change in level, and rate of change of temperature, and the cooling water temperature. And then from there, I'm getting much simpler models, and models that are much quicker to train and that are more accurate than when I used all 13 of these features. But in the next cycle, when I talk more about the wrapper methods, I'll be sharing some of my results from these experiments that I'm currently conducting on these methods. Yes, that is it. That concludes my presentation. I'd like to hand over back to the chair.
Thanks very much, Philani. The paper is open to questions. Sid?
Yeah, that was a nice presentation, Philani. Just one question I had, which you mentioned, you're basically trying to find the sensitivity of your input variables to your output, and then you want to select the variables that are maybe like the top n variables that have the highest sensitivity and use them. And so that's your filtering method. But yes, then you said you noticed that one variable may have a very low sensitivity, and then when you take that out, the neural network may perform not as good as when the variable was in there. So the question, so my question is, are these variables additive in the sense that, well, I think that's a property. When you have the sensitivity of one variable plus the sensitivity of another variable, is that equal to the sum of the sensitivities? Because what if it's there's like this pairwise relationship where the union of those variables is greater than the sum of it, and then like the sum of the sensitivities, and then that number can go like much larger. So what if 3 is greater than 2? So yeah, so hope you understand what I was saying. So like, how are you going about that? Because like it seems like just with these correlations, and I'm sure you applied more sophisticated correlations, it seems like this is just analyzing one-to-one, relationships between one input to one output.
No, that's a very good question, and that's one question that that also came that I really had when I was working through this. There is another method. It's called mutual information. So what mutual information does, I think I'll also just cover it in in the next lecture, is it does account for that. So what it does is it works on distribution, additive distributions of the different features, because it evaluates the probability distribution of of all the features. So it's more like how can I say, it's more like an additive search method. So that question is actually solved by the wrapper method. So what the wrapper methods do is, it's very hard to tell to tell the mutual relationships beforehand, how two of them affect, because there's so many permutations here. So you have 13 variables. What if the combination of this is much stronger than the combination of this variable and that variable, and so forth. So what can be solved with that, how that problem can be solved is through the wrapper methods, where, for example, the wrapper method, it starts with one variable, okay, which is the one variable that is strongly models the target variable. Then it adds the second strongest variable, and then the third strongest. But then as it adds the variables, if there's no increase in accuracy, then it removes that variable. So to solve that problem, that would require an exhaustive search. These methods, they are more like introductory, for you to see the relationships offhand. And if, for example, you do encounter something like that, where you see that even though you use this table to select variables, but your model is not accurate enough, then you can actually start adding the next most correlative variables to see whether it does result in an improvement. But then that, of course, would then end up being the wrapper method, where you are permuting the different variables to see which combination is the best for your target variable. So to solve that particular problem, the wrapper methods would be the approach that you would you would have to pursue for that. And that is basically that. Your question actually outlines the limitation of these methods. They do work in some instances, and in some instances where those additive relationships do exist and they are not captured, then that's where you would go to to the next step, and you start having do some experiments on the actual machine learning model. I don't know whether that answers your question.
Okay, so thanks for that. If I can come in there, you see, to be extracting features variable by variable, there are sophisticated linear algebra methods around this. So, and some of you have, we are using it in your project. So singular value decomposition helps you transform your input space with respect to your output variable, such that you maximize the sensitivity. So if you think of it, you've mentioned, there's one variable that correlates to some extent, and another variable sometimes correlates with the first variable. And so you see, in singular value decomposition, you actually transform your input space such that you create a new set of variables, and those are a linear combination of the existing variables. So you have your variables that are well understood, like you mentioned control valve setting, and then temperature and pressure and level and so on. So those are things in the real world we can understand. However, in singular value decomposition, what you do is you find linear combinations of all those variables, which gives you a new basis set. And so each basis vector, or each dimension, is some linear combination of the real variables. And there you totally butcher it, right? You don't care about the fact that you are taking a linear combination of temperature and pressure and level. You don't respect the units at all. You just treat them as numbers. But still, what it does is it maximizes your sensitivity of your output variable to an orthogonal set of vectors. And it does it in such a way that the very first vector exhibits the maximum sensitivity. So your output has the maximum sensitivity to the first one. And then the next in the orthogonal set will have the next highest sensitivity, and so on. And so you transform an n-dimensional space. So let's say you have n features. You transform your n-dimensional space into another n-dimensional space. So it's linearly dependent on that one. And you even get a kind of ranking. So the eigenvalue that you get as part of these transformations actually helps you rank which vector contributes what level of accuracy to the model. And so you can almost pick your accuracy. If you say, I want 92%, then you just look for how far down the eigenvalue list you want to go until you meet that. And then that fully defines for you how many of those new variables to use. So singular value decomposition. I think it's something that I do want to produce a lecture on, and but maybe you'll also cover it in this series. So and it's something I've mentioned to you before. Have you thought about incorporating SVD, and is the plan to progress to using that way of doing your feature selection?
Yes, yes, I was considering SVD, but the only issue as I had with SVD was with the interpretability, because as it just goes to an alternative dimension, feature space or dimensional space that you can't really call it, refer to, use units on it. So my idea was just to take a look at methods where I can still keep the traditional chemical engineering units and so forth in it, but then depending on the outcomes, maybe down the line I might actually consider evaluating the best method here compared to how it would relate to the SVD setting.
Well, it is an important point, the interpretability of the result. So how much do you actually learn from the model? But it talks to your objective. If you just want the best possible model in terms of performing at a high accuracy, then in that sense, you might not care about the interpretability. But if you are trying to learn from the data and understand how the system operates better, then it's more of a concern. But having said that, with SVD, I have read papers where people have actually used SVD for interpretability. So there was this interesting paper where they were trying to predict which representative in the House of Representatives in the US political system, they were trying to predict which way they would vote on a particular bill. And they ran SVD on that, and they got out a linear combination of the characteristics of the representatives, and you can still interpret that result. It shows you which variables are ranked highest in the first linear combination, and you might find it's something like whether you are left wing or right wing, or whether you are, so it actually does, it can be used for interpretation as well. So so it's not the case that even though it transforms into this alternate set of axes, it's not the case that you still can't do some interpretation there. Right. So I guess I'm just a big defender of SVD, and yeah, I think it's almost required knowledge as part of our linear algebra development. And for us in machine learning and artificial intelligence, linear algebra, in spite of the modesty of the name, is one of the most important things that we can spend our time on. And SVD is kind of the flower of linear algebra. So I think we must definitely look into this area and dedicate some seminar time towards that as well.
Okay. Thank you, Prof.
Thanks. Any other questions or comments there? Zamishka?
Okay. Yeah, if I could just weigh in there, because Prof knows we actually were studying SVD and principal component analysis, and I actually brought down 17,696 dimensions down into 3. So it's definitely a very, very powerful tool. And with the accuracy, I actually checked the accuracy recently. Obviously, with using every single dimension, in my case, I got 100% accuracy, but bringing it all the way down into a sort of more manageable size, which was 3 dimensions, it was a 97.2% accurate. So so bringing it down into a completely workable space, it makes it super useful. And actually with yours, I thought that principal component analysis might be useful to you, because you mentioned that you're looking for correlations between your variables, where one increases, the other one may increase. Because here I saw there was a strong correlation between the feed flow rate and I think the pressure. So what principal component analysis does is there's the definition here. It finds all the features that have the highest possible variance and the lowest possible covariance. So you can sort of delete one of those variables. So if you have feed flow rate, you can assume that, not assume, but that the pressure will increase as well. So you don't need to consider both dimensions when you sort of picking your important ones. So that's what I thought that might be useful.
Okay, thanks a lot. I was definitely, I've done, read on it before, but yeah, I think I just need to go back again and take a look at it and see how maybe it could just stop me. Yeah, it could maybe be the solution for me, instead of going through this exhaustive search route. Maybe, I think it would be good for me to just take a look at those and see what outcomes I can get from them. Thanks a lot.
Great. Other questions and comments?
Hi, everybody. Thank you, Philani, for that presentation. I think for me, it's very relevant at this point, because even at our last meeting with Prof, I'm still trying to figure out which features, and how do I select my features? Okay, so I'm going to ask a very basic, maybe a bit silly question. It just to come up even with that set that you started with and eliminated from, how did you go about doing that? I know it's a basic question, because I've got all these articles and they use different features. Some of them will just use weather, the outdoor weather, the indoor weather. Some of them will actually use actual building attributes, the size of the building, the compactness of the building. So it really varies. I even wasn't sure whether I just need to take all those articles, make a list of all the feature, all the variables that they use, and then work from there. That's the first question. The second question is, okay, so most articles use the 2 methods that you showed. Some of them actually use the correlations, use both of them in all articles. But I came across one article that uses a loop method. I don't know if it's already discussed in the meeting, because I don't know the actual terms for now. I'm still learning the terms. So they'll add the variable, and then they'll see how it affects the model, and then they'll add the next variable, and then they'll kick out, some variables get kicked out. I wanted to ask if you've come across that. So those are the 2 questions I have.
Okay, just to answer your first questions regarding the selection of variables. It's I think has to do with using domain knowledge, a bit of domain knowledge as well. In my case, I looked at, a particular reactor. I looked at all the, the variables that were measured, and, and then because reactor is like, it was a block, and I basically specified a boundary around it, and I said, okay, whatever is happening inside here, these are the variables that I'm going to consider. Ideally, the more variables that you have, see, the thing is, you want to have variables that are measured and are measured accurately. As long as a variable is measured and measured accurately, then add it, because it's sometimes you'll never know how they they relate, whether they would relate or not. But then now there's another issue with causality and correlation. That's another issue that you need to be careful of. So that's why in this variable selection process, you do have to use some domain knowledge, because if you, for example, I had this big plant, but if I had to use, I think the plant had around 52 variables, and then when I was playing around with this, it had like a variable that was somewhere far off that had nothing to do with the reactor, but he was telling me they're very strongly correlated with each other. And then using that information, now it was going to mess up my model. So to answer your question, one is do use just make sure you use variables that are measurable and and can be measured well, but also do use your domain knowledge and common sense in generating your initial list. In most cases, if I'm 100% sure that, hey, this variable is really out of the scope of what I'm looking at, then I remove it. If you're not sure, then you add it to the list. To answer your second question, is regarding the loop method. I think the approach that you are discussing is the wrapper methods, where you have your machine learning model at the middle, and then you choose, usually it's a recursive, they call it recursive addition or recursive elimination. So let's say you have 4, they remove, you want to remove one of them, you remove one, and you remove the one that results in the least drop in performance, and then you keep removing. Then you reach a point where when you remove another one and then your performance really drops, then you stop there. Then recursive addition is when you add one by one and you add combinations. So that falls under the wrapper methods category. So that is where you do a search. That's the loop aspect that you are talking about. I don't know. I hope that answered your questions. Okay.
Yeah, thanks. And I think it was a good comment to make about using domain-specific knowledge, because there is that growing sense, if you follow the literature and also popular articles about the success of machine learning, in that it turns out that people who have domain knowledge and who know machine learning, that combination is what leads to success. That it's not machine learning in itself that leads to the success. Yeah, I think that comment on using your domain-specific knowledge judiciously with your machine learning, or machine learning by itself, if you trust it too far, you're liable to make really problematic errors. So yeah, I think that was a good comment there. Okay, any other questions or comments? Okay, Sudain.
Yeah, so I had my hand raised, but then I thought about my question and then I lowered my hand and I figured, why not? Let me just ask it anyway. So I was thinking about the application of this as a whole towards my topic or whatever the case may be. So would it be possible to generate some kind of table like this, but maybe as a surface plot with more dimensions? And why I'm asking is because you see the weight of the correlations between variables as you've represented here, like even so on the y-axis towards the bottom, you have like the change of pressure with respect to time or whatever the case may be. So you started introducing changes on that axis, and it's also on the x-axis as well. But so in the case of databases where you have like, like literally possibly thousands of tables or tens of thousands of tables, you kind of get the gravity of correlations between variables may be a bit more challenging, because I know especially with ontology engineering, what you're trying to do is, if you're trying to use correlations to give semantic joins between aspects of text or a resource description framework, it's a bit more complex, because I looked at word vectors or whatever the case may be. So I started looking. So I think one of these correlation formulas you mentioned, I looked at before. But like you were saying, the interpretability of it is not too feasible, or at least that's what I found earlier on. So, with this selection framework, is it possible to, what are the limitations as far as, okay, if you're working with variables from multiple sources, like, does it work well on tables of like with thousands of points or not?
Okay. The thing is, I think the first thing is, of course, you can have. I mean, if it's a question about scalability, yes, it can work with a lot of points. But then one thing you raised as well, I mean, a lot of features. So it's not a matter of points. The more points you have, actually, the more accurate the relationship, the correlations would be described. If you're working with thousands of features, yes, that's where the limitation, because I just did a manual. See, this manual approach that I did, that's the first limitation. I could do it here because I'm working with few points, but then once it gets into thousands, then it becomes a bit impractical. Yes, you can have some if statements, but as well, that's not very practical. It can you can make it practical, or sometimes it can be impractical. And I don't know, you spoke about more like a surface plot, because another way I was looking at it is about, I think it's distributions, where whether with the distribution of one variable, does it affect the distribution of another, and does the distribution of a combination of variables overlap with the distribution of another. That is, that's when you get going more into information theory and so forth. I think that's sort of an alternative. There is this concept called mutual information. It's a information theoretic based concept. But I haven't read much into that. But I think that could be one way where you could represent this more surface based representation of the relationships, and you look at how the distributions relate to one another.
Well, on that, of course, Philani, you haven't mentioned your earlier work where I guess if you think of a table of data, most of our early years were about reducing the number of rows, right? So you can reduce row-wise because you have lots of repeated data points. You have many rows that are giving you the same information. So a lot of the early work was to reduce the table this way. And in this presentation, you are talking about reducing the table that way. Now, as Amishka mentioned, 18,000 features compressed into 3 features, and she only lost 3% accuracy. That's the kind of compression you can get column-wise. And in fact, there are some applications where, image compression. So SVD is often applied in image compression. So, and in some of those, it's the individual pixels. So the color value behind each pixel, that's actually what's being compressed. So if you think of each pixel as a different feature, that gives you an idea about how big it can be millions of features. So it can be crazy column-wise and row-wise, but you can compress it and you can extract features. So yeah, so it's quite amazing the things we can do today. So, but okay, I guess we are out of time on the questions. So in terms of comments on the presentation itself,